So in this question, dice is thrown 5 times, and what we're asked to do is calculate the probability of obtaining exactly 1/6, at least 1/6, and we're also interested in the theoretical mean and variance of the number of sixes obtained. Now this is a dice question, and it is a dice is thrown 5 times. Okay, now if you are familiar with the binomial distribution, you will see that we can frame this question quickly in terms of the binomial distribution. Now, if you were to try to do this without using the binomial distribution, for example, using probability trees, the question will get too complex because we have to take into account too many possible eventualities of the dice rolls. Okay, so we throw a dice 5 times. It's just too many sort of possible outcomes to draw properly on a probability tree. So this problem is just not tractable or not solvable with any significant degree of ease other than using the binomial distribution. So how can we sort of reconcile this, what we're asked here, with this idea of the binomial distribution? Well, first off, let's consider what the binomial distribution is about. Now, I'm going to sort of glance over it here. If you're not familiar with it, probably best sort of stop the video here and go look at stuff about the binomial distribution. So, the binomial distribution is characterized essentially by two things: the number of trials, and here we're going to call that number of trials, n. Now here it's a number of trials or a number of experiments, to use the sort of the basic statistical definition of an experiment, where we're trying to sort of find out about an outcome. Here the number of trials here is the number of times we roll the dice, and that is 5. Okay. So in a binomial experiment, we're looking at two outcomes, and we're interested in what a success is and what a failure is. So here we're interested in this the outcome of throwing a 6. So the success is a 6. And finally, we're interested in the probability of success, P. And if you throw a die, what is the probability of throwing a 6? Simply 1 in 6. Okay, so those are the things that characterize the probability distribution, the binomial distribution. Now, I have a little formula here beside there as well, and generally this formula here is given in the exam paper, or it's not too bad to remember, but essentially I'll just write it out again here. N choose k, p to the power of k, times 1 minus p n to the minus k. Okay, now, so that's just writing out the formula there again, just to make it a bit clearer. Just as a remark, n choose k might also be written as, I'll just write it up here in the top corner, n choose k. So it's quite often some books will, some material will have the notation like that. That is the binomial coefficient. It's also, we might call it the choose operator, binomial coefficients. And we'll come to that now shortly. So the k is just a sort of a matter we can sort of discuss later on, but we have n there and we have p there in that formula, and we also have the right numbers here: probability of success and number of trials. So let's try out using the binomial distribution for here. We're interested in the probability of exactly 1/6. So x is the number of successes. I'm going to call that x, and that means number of successes. Whoops, I sort of made a dog's dinner of that. Number of successes in n trials. Okay, or in this case we're interested in 5 trials, so n equals 5, so I'll just cross that out in 5 trials. So this would sort of say that the probability of the number of successes in 5 trials equal to 1 is what we're looking for. Probability of x equal 5, number of successes in 5 trials equal to 1. Okay, that's exactly what we're looking for. So earlier on we had k here, and that's just essentially the number of successes, or a sort of a placeholder for this. So probability of x equal to k is, so essentially k is 1 here. So what we're going to do here is calculate 5 choose 1. 1 is also the number of successes, k, and n minus k is 4. 5 minus 1 is 4. So using this formula again here, let's just sort of write it down here at the bottom. Actually, I'll just take a load of this stuff out so I have more space. So we have decided here that n is going to be k. So 5, oh sorry, let's go back that again, scrub that out. 5 choose 1. Okay, not p is 1/6, so 1 over 6, and k is 1, so the power of 1, and 1 minus p essentially was 1 minus 1 over 6, we'll just call that 5 over 6. And we have n minus k there, that's 5 minus 1, so we have 4 there. Now these bits here should be relatively straightforward to compute by calculator, but the binomial coefficient requires a bit of extra work. Okay, so that's not 5 divided by 1, it's from 5 choose 1. So the correct formula for 5 choose 1 is this. I'll just write it again here just beside. Actually just write it in blue, I'm using red too much. N choose k is computed as n factorial over k factorial times n minus k factorial. Okay, so 5 choose 1 is 5 factorial divided by 1 factorial times 5 factorial. Now I'm going to sort of, you can sort of work this out, but you'll probably find very soon, quickly, that the answer there is 5. So probability of x equals 1. We have, I'm just going to go back to my previous slide here. We know this is simply 5 here times 1/6 times 5, 1 over 6 to the power of 1 times 5 over 6 to the power of 4. So it's very straightforward enough calculation. Just working it out, it's just a bit of calculator work, 0.401. So the probability of getting exactly 1/6 is, in 5 dice rolls, is 40%. The second question is, what's the probability of obtaining at least one head? Okay, now it's very important here to sort of think, at least one head, what does that mean? It sort of says, it means one head, two heads, sorry, 1/6. I've this is a mix up in the question. So bit of a typo there. you get, when you're doing these probability things, you get sort of mixed up between dice rolls and coin tosses very quickly. So, what's the probability of obtaining 1 6 is the complement of obtaining 0 6s. Okay, so the question is, what's the probability of obtaining 1 6 in 5 dice rolls? 5 dice rolls, yeah. So it means 1 dice roll, 2 dice rolls, 3 dice rolls, 1 6, 2 6s, 3 6s, 4 6s, or 5 6s. Now there's only 5 dice rolls, so you can only get, that's the maximum number of 6s you can get in 5 dice rolls. Now we could, they're all mutually exclusive, okay? And we could compute all the probabilities, but an easier approach is to go and find out the probability. The only outcome that's not allowed in this at least 1 6 scenario is the probability of 0 6s. So the best approach here is actually to use the complement rule. Okay, so the probability of x greater than or equal to 1, that at least 1 6 if not more, that is the complement of no 6s. Probability of no 6s. So what is the probability of no 6s? Well, we're going to use the same formula again. Now this time around we're going to let k equal to 0, just using the exact same approach I've done the last time. But just as a remark, I'm going to sort of point out that 0 factorial, when you're calculating this here, is equal to 1. Okay, so the probability of x equal to 0 is 5 choose 0, from 5 choose 0. Remember, k is 0 now, so 1 to the power of 6, 1 over 6 to the power of 0, times 5 divided by 6 to the power of 5. N minus k is 5 minus 0 equals 5. K is just 0. Okay, now just as a remark, as a second remark actually, I'll just write this up here. Anything to the power of 0, let's say x to the power of 0, anything is 1. Anything to the power of 0 is 1. This is just a general mathematical rule. Okay, this part here necessarily automatically becomes 1. Okay, 5 choose 0, that's from 5 choose 0, that's 5 factorial divided by 0 factorial times 5 factorial. Remember that 0 factorial is 1, so we have 5 factorial, actually I'll write it out here, 5 factorial over 1 times 5 factorial, and that is 5 factorial divided by 5 factorial, that's just 1. Okay, so the answer we get is 1 times 1 times 1. So the answer is actually 5 divided by 6 to the power of 5. This actually also becomes 1. So when you calculate this part out, you should get, let me just check that here for a second. Pause that. Yeah, sorry, I just wanted to double check because it turns out to be the same number as in our last example, just by accident. So the probability of x equal to 0, that no 6s, is also equal to 0.401. Now remember, we're looking for the complement of that, 1 minus that, so it's 1 minus 0.401. So the answer we're looking for, the probability of x greater than or equal to 1, the answer to that part there is 0.59. I've probably just used a bit too much highlighter there. 0.599. Okay, there's a little bit more to this. No, I'll leave it there. The question we were asked was obtain the theoretical mean and variance. So essentially this is a bit of bookwork. The theoretical mean of the binomial distribution is n times p. Essentially, for 5 rolls of a dice, what is the expected number of 6s you will get, and the theoretical mean, which we're going to denote as E of x, oops, done that again, is theoretical mean for the binomial distribution is simply n times p, and that is 5, which is the number of trials, times 1/6. It's the probability of a success, so it's 5/6. Okay, and the variance of x is n times p times 1 minus p, and that is 5 by 1/6 by 5/6. So the answer to that is, bit of calculator work, 25/36. You can decimalize that as well if you want, have it 0.833 and so on, but we'll leave it there. Long out video, 16 minutes.